So this is the second part of Chapter 9 in our talk on cache memory and virtual memory. So in Part 1, we talked all about cache memory. So in this section, we're going to begin in Section 9.5 over virtual memory and memory management. So memory management is the point at which the operating system and the hardware kind of meet, right? That's the center. And it's concerned with managing the main store and the disk drives. And in many ways, the memory management is a type of scaled up cache technology. So when computers first appeared, because just like they just appeared, an address generated by the computer corresponded to the location of an operand in physical or real memory. And even today, if you have like 8-bit microprocessors and controllers, they don't generally use any type of memory management. So the logical address that's generated by high-performance computers and like PCs and workstations, and probably what you're using to watch this video on, is not the physical address of the operand accessed in memory. So if we think about our instruction set, I'm sorry, I broke the captions. I want to make sure and keep the captions. I get a lot of requests. All right, so let's consider the instruction right here, the LDR, that copies the contents of the memory location pointed at by register R3 into register R2, and assume that register R3 contains some kind of value, so like this value right here. The data might actually be copied from, let's say, a memory location address in the DRAM-based main store. So the act of translating this value from that memory address is memory management. So in this section, we're going to talk about why memory management is necessary and how basically it's achieved. So virtual memory is a term borrowed from optics. So it describes where an image that appears to be in a place where it's not. For example, a telescope might make an object appear as if it's right in front of you when it's really a long distance away. Virtual memory space is synonymous with logical address space and describes the address space that can be accessed by a computer. So let's say we have a computer with a 64-bit address and pointer registers. So we have 2 to the 64-byte virtual or logical address space, even though it may be in a system with only 2 gigabytes, which is 2 to the 31, of physical main store memory. And really, memory management goes back to the 1950s and 60s and describes any technique that takes a logical address generated by the CPU and translates it into the actual physical address in memory. And so really what memory management allows is the physical address spaces of DRAM and the hard disk to be seamlessly merged into the computer's virtual memory space. So let's talk about memory management. Computers using operating systems like Windows or Unix make extensive use of memory management techniques. And so we can take a look at this figure that describes the structure of a system with a memory management unit, often called an MMU. In principle, it's a very simple arrangement. We have the logical address from the CPU, and it's fed into the MMU. So we can see logical address fed into the MMU. It translates it into the physical address, and then that's the operand in memory, right? And so then we can put that into memory. And this translation really involves just a lookup table that converts logical addresses into physical addresses. And it's a very large table because really, I mean, how else would you do this? A large table is required to translate each logical address into a physical address, and memory space is divided into what are called pages. And each new address is on a logical page. So each logical page is translated into the corresponding address on a physical page. Uh-oh, I broke my subtitles again. There we go. Let me say that again. So a logical page is translated into the corresponding address on a physical page. So a page is typically 4 kilobytes. So we can see an example here. If the page size is 4 kilobytes and the processor has a 32-bit address space, we can see that the logical address here might be this address here. And so the size of the processor's logical address space is independent of the addressing mode used to specify an operand. Nor does it depend on whether a program is written in a high-level language, assembly language, or machine code. So in a 32-bit system, the instruction, like this, LDR R4 R6, lets you address a logical space of 4 gigabytes. So no matter what technique is used, the processor cannot specify a logical address outside of this 4 gigabyte range, simply because the number of bits in the program counter is limited to 32. So physical address space is the address space that's spanned by all of the actual address locations in the processor's memory system. This is the memory that is in no sense abstract and costs real dollars and cents to implement. And so, in other words, the system's main memory makes up the physical address space. The size of a computer's logical address space is determined by the number of bits used to specify an address, whereas the actual quantity of physical address space is frequently limited only by its cost. So basically, how much money does it take to put more memory space on a chip, and then how much will a consumer pay for that? So we can see this relationship of why a microprocessor's logical and physical address spaces may have different sizes. What is a little more curious is why a microprocessor might, for example, employ memory management to translate a logical address to a physical address. And so really the fundamental objectives of memory management are to control systems in which the amount of physical address space exceeds that of the logical address space. So if you have an 8-bit microprocessor with a 16-bit address bus and a 64 kilobyte logical address space and 2 megabytes of physical RAM, right? We have to manage all of these different sizes to control systems in which the logical address space exceeds the physical address space. So if you have a 32-bit microprocessor and 4 gigabytes of logical address space, and if you have 64 megabytes of RAM, so in this case, the logical address space is bigger than the physical address space. For memory protection, and we haven't really talked about memory protection so much, but this includes schemes that prevent like one user from accessing memory space that's allocated by another user, from letting programs basically reach into memory space being accessed by other programs or by the operating system, which would cause kind of access violations. Memory sharing, where one program can share the resources of another program. So if they have common data areas or common code, then you want that kind of behavior. So this basically facilitates that. Efficient memory usage, in which the best use can be made of the existing physical address space. So we're not just doing things and putting stuff all over the place and making a mess. And freeing programmers from any considerations of where their programs and data are to be located in memory. Because if you think about you, the programmer, having to think about where our variable memory actually came from, this would make our job so much harder. So the programmer can use any address he or she wishes, but the memory management system will map that logical address to an available physical address, so we don't have to worry about it. Now, a real memory management unit may not attempt to achieve all of these goals, and really, the first two are mutually exclusive. The second goal, right, dealing with logical address spaces, is especially important to designers of what we have now, which are 64-bit systems. And when memory management is applied to this problem, it's frequently referred to as virtual memory technology, and virtual memory is almost synonymous with logical memory. So this problem of available physical space being smaller than the processor's logical address space is really caused by economics, and it's always plagued the mainframe industry. And so in like the late 1950s, when mainframes were available with large logical address spaces, but they were restricted to like tiny 2 kilobytes or so blocks of RAM, then a group of computer scientists at Manchester University in the United Kingdom proposed this memory management technique now known as virtual memory to deal with this situation. And so a section of logical or virtual address space is mapped into the available physical address space. So just to make sure that you're not getting tripped up in the terminology, we're literally talking about there's a section on your hard drive, and forget about whether we're talking about platters or solid state. There is a section of your hard drive that is carved out by your operating system and used in place of your DRAM, right? That is what we're talking about. So don't be confused. And so, like I said, the section of the logical or virtual address space is mapped onto the available physical address space. And we could see this right here in this figure. And so if we have this example, right, 256K section of logical address space, and then we have this range right here, and it's mapped onto physical memory in this range, right? We can kind of, this is like just a visual of kind of how this would work. So we have 16 megabytes of RAM, so here's our CPU address space, and then you have 256K physical address space, and so it would fit within this range that we've given it here. So as long as the processor accesses data in the logical address space that's currently mapped onto the existing physical address space, all is well. And we've been doing this since the 1950s when these people invented virtual memory. And really, we can just assume at this point, right, that an address from the CPU is passed directly unchanged to the system's address bus. So when the processor generates the logical address of an operand that cannot be mapped to the available physical address space, that's when we have a problem. And then the solution to this problem that the people at Manchester University adopted was pretty simple. So basically, whenever the processor generates a logical address for which there's no corresponding physical address, the operating system just stops the current program and deals with the problem. Because the operating system is the one responsible. It's going to go fetch a block of data containing the desired operand from the disk store, place this block in physical memory, may overwrite any old data, and then tells the memory management unit that a new relationship exists between this logical block and the physical address space. So the program or data is held on disk, and only those parts of the program currently needed are transferred to the physical RAM. And the memory management unit, its whole job is to keep track of the relationship between those logical addresses generated by the processor and that of the data currently in the physical memory. And this whole process, we say that the solution is delightfully simple, but the whole process is very complex in its details, and it requires a lot of harmonization of the processor architecture, the memory management unit, and the operating system. And people dream of simple memory management systems because they have nightmares about how the real ones work. Now, obviously, it works, and it's worked great for decades, and we don't have any other better solutions right now of making this work. And so the next time your operating system has some kind of fault and it's related to virtual memory, page files, or something like that, this is what's happened, is the operating system did not properly do its job, or the memory management didn't properly do its job, and something happened between where the program needed to get or was trying to get its data and was passing those addresses to the processor, but either the processor didn't have the logical address for which there was no corresponding physical address, or the operating system didn't give us the block, and something maybe broke down there or didn't communicate it correctly to the memory management unit. And so there's a lot of ways that this can go wrong. It is definitely a complex science. So we can't even say it's an exact science because it is very complex and requires a lot of moving parts to make it work. So let's talk about our memory management and multitasking. But before I go any further, I want to talk about virtual memory for just a second. So really, virtual memory systems, they serve 4 different purposes. And I want to make sure and talk about this. So they support systems with larger logical memory spaces than physical address spaces. They map logical addresses onto physical addresses. They allocate physical memory to tasks running in logical address space. And they make it easier to construct multitasking systems. And this is why I wanted to kind of address this before we talk about memory management and multitasking, because it would be foolish to pretend that justice can be done to the topic of virtual memory just from a beginner's standpoint. Again, I can stress how complex this is. Virtual memory systems are designed by teams of designers and programmers and require many hours to produce because the management of virtual memory is not only complex, but it's found almost exclusively in systems with multi-user or multitasking operating systems, which maybe you have noticed is just about everything. So let's talk about multitasking, because multitasking systems, really the whole idea is that it executes 2 or more tasks or processes concurrently by periodically switching between tasks. And so we're not really doing more than one thing at the same time, almost like when humans multitask, right? If you try to do a bunch of different things all in the same hour, you're not really simultaneously doing stuff at the same time, right? You're just switching from task to task, and maybe you're just taking advantage of downtime. So I know I multitask a lot as a software developer. If I have a long build time, the minute I hit build and I know it's going to take a couple of minutes, maybe I'm off reading something, research something, watching a video, maybe I'm looking at something else, or I'm reading my email, or I'm on Twitter, right? And so once the build is done, then I switch back and now I'm working on this, and then maybe I find a bug, and so then I work on that. And so you're really switching between tasks. You're not really doing processes concurrently. And so multitasking is viable only if several tasks reside in main memory at the same time. If the tasks had to be transferred from hard disk every time that they run, then the time required to swap in and out of a new task would be really prohibitive, and we wouldn't be able to run computers as fast as we do. So if we take a look at this figure here, figure 928, this demonstrates how logical address space is mapped onto physical address space in a system where we have 2 different tasks going on. So we can see task A over here and task B down here. We've got program, stack, right? Private data, some shared data, and then we have this physical address space that's going on over here. And so tasks A and B reside in physical memory at the same time. And then each task has its own logical memory space, and it can be accessed or can access if there's shared resources. We can see how they can share each other's resources if that's the point of that shared data. But the programmers of these 2 programs, task A and B, are entirely free to choose their own addresses for the various components of their task. And so consequently, A and B can each access, right? They can each access their own areas of data at the same time and the same structure in physical memory, even though they use different logical addresses, and they can even share shared data even though they use different logical addresses. And each task is aware of only its own copy of the data that it might share with another task. And so the memory management unit is the one that maps the logical addresses chosen by the programmer. And when I say chosen by the programmer, I know, and you hopefully know as a software developer, you're not choosing anything, right? When you create variables, all you get to choose is what do you want to name it as its alias name, and then what data type is it. But essentially, you are choosing, because when we choose a data type, we're choosing a size of memory space that we want to use. And so what that really comes down to when we say that you're choosing, you don't have to think about, the programmer does not have to think about the logical addresses or how they map onto the physical memory space, or the fact that they may or may not be together in the same block. The operating system is then responsible for setting up the logical to physical address mapping tables. So as a software developer, we're really abstracted away from what is actually going on with memory. But that's why a course like this is so important, is to really understand what is going on with the system and the memory, and how my application might be affected, or how my application works in this kind of environment. So whenever we have a new task that's created, the operating system is going to inform, or it is informed, of the task's memory requirements. And so then the operating system searches the available physical memory space for any free memory blocks that are of the right size, and allocates these to the task. And so you can imagine that after a time, the physical memory space is going to become very fragmented, with the various physical blocks belonging to each task kind of all interwoven into a little pattern. And a good operating system, now, I don't want to get into a debate about what a good operating system is, but a good operating system will attempt to perform memory allocation efficiently and should not permit large numbers of unused blocks in physical memory. So the way in which this fragmentation is dealt with depends on the type of memory mapping implemented and on what operating system is doing the work, because they all kind of do this a little differently. But a powerful feature of memory mapping is that each logical memory block can be associated with various permissions. So, for example, if we have we can have memory that's like read only, or write only, or accessible only by the operating system, or accessible by only a given task, or shared between groups of tasks. So by ensuring that physical memory blocks can be accessed only by predefined tasks, you can then ensure that one task cannot corrupt another, right? You can't just accidentally go in there and mess with something and then cause all kinds of havoc. So there's two fundamental ways of implementing memory management. One uses fixed size blocks of memory that I previously talked about, which are called pages. And the other has variable size blocks of memory called segments. And so we're going to start by talking about address translation, because memory management provides us with two distinct services, right? To map logical addresses into the physical available space. And the second function occurs when the physical address space runs out. So that logical to physical address mapping cannot be performed because the data is not available in the RAM. And so if we take a look at this figure, we're looking at how a page memory system can be implemented. So remember, pages are fixed size blocks of memory that the operating system just plucks out and allocates. And so this example uses a microprocessor with a 24-bit logical address bus. We can see 512 kilobytes of memory, and the 24-bit logical address from the processor is split into 16-bit displacements that are passed directly to the physical memory, plus an 8-bit page address. So we can see 24-bit logical address, split 8 bits, 16 bits. So the page table over here gives us a page address, And the page address specifies the page, one of 2 to the 8, which would be 256 pages, currently accessed by the processor. The displacement field of the logical address access is one of 2 to the 16 locations within a 64 kilobyte page. So the table contains 256 entries, and here I can make this a little bigger. Let's make that a little bigger. The page table contains 256 entries, one for each logical page. And in this example that we see in the figure, the CPU is accessing the 8-bit logical page address, and we can see this right here, ending in 3 ones, right? Takes us down here to the page table, that page address. And each entry contains a 3-bit page frame address that provides the 3 most significant bits of the physical address. So we can see that here. And so in this example, that physical page frame, right, 110, and that logical address has been condensed from 8 plus 16 bits to 3 plus 16 bits. And so we get this kind of logical address instead of a much larger looking address like this over here. And so although there are 256 possible entries in the page frame table, which is one for each logical page, the physical page frame address is only 3 bits, which limits the number of unique physical pages that we can have to 8. And consequently, a different physical page frame in random access memory cannot be associated with each of the possible logical page numbers. Each logical page address has a single bit. So it's an R field, and we can see this resident R bit in the table here. And if the R bit is set, that page frame is currently in physical memory. If the R bit is clear, the corresponding page frame is not in physical memory. And so the contents of the page frame field is basically meaningless. So whenever a logical address is generated and the R bit associated with the current logical page is clear, an event called a page fault occurs. And again, I talked about how it's a pretty common operating system blue screen type event. Once a memory access is started, so once it's began and it attempts to access a logical address whose page is not in memory because the R bit was found to be clear, the current instruction has to be suspended because it can't be completed. The data that we need isn't here. And when this happens, the operating system is designed or should intervene to deal with the situation. It doesn't always work, depending on what has actually caused this fault to happen. And although the information the CPU is attempting to access is not currently in the RAM, it is located on the disk. And these kinds of faults happen, I don't want to say all the time, they happen frequently, but in most cases, the operating system just goes and retrieves the page containing the desired memory location from disk, loads it into the physical memory, updates the page table accordingly, and the suspended instruction can be executed. Do you notice when this happens? Probably not. It happens fairly quickly. Now, if you're all of a sudden your program kind of hung for a second, could be what's going on. You can go find in your Windows logging, and I'm sure in Mac's operating system as well, a log of things like page faults that occur so that you could see how frequently this is happening. But in the case where we actually realize it's happening and we get like a blue screen event and all of Windows halts and we can't clear it, sometimes those are generated because we've got some kind of hardware problem, we have had some kind of interference, or something was just completely unrecoverable to where the operating system was not able to retrieve that page and load it into the physical memory. So clearly, an effort is involved every time a page fault occurs, and it's a rather large effort. And as long as we're not generating like a ton of page faults and the system works well, and remember it works because of that phenomenon we talked about, the locality of reference. And so most data is clustered so that once a page is brought in from disk, the majority of memory accesses are going to be found within those pages. And so we don't necessarily have to go back to disk as often. But when the data is not well ordered or when there's many unrelated tasks, the processor ends up by basically spending nearly all of its time swapping pages in and out, and the system kind of slows down and can grind to a halt. We actually have a technical term for this situation, which is called thrashing. And so thrashing refers to any computer activity where accessing a resource just repeatedly leads to a catastrophic decrease in performance. It actually rarely refers to an actual situation in which virtual memory system breaks down because of the need to reload pages. A lot of people just use thrashing as any time the system is like significantly slow or hung, but that is, of all things, the technical term. So the arrangement that we've been looking at in the previous example is really impractical in modern high-performance processors. We've been kind of looking at it from a simplistic way, as we've been doing throughout this course, to make sure that we really understand what we're talking about before we add any complexity. But let's suppose that we have a 32-bit computer and it uses an 8 kilobyte page that's accessed by a 13-bit page offset. So the offset is the location within a page. And so if we do the math, 32 minus 13 equals 19 bits to select one of 2 to the 19 logical pages. And so it would be improbable, or maybe impossible. I like how the author says impossible, to construct such a large page table in fast RAM. And so this is basically the same problem that is faced by designers of memory cache, but we can take a look at this figure here that describes how it is possible to perform address translation without the need for massive page tables by using multi-level page tables. So the logical or virtual address from the computer is first divided into a 19-bit page number and a 13-bit offset. So we can see 19 bits, 13 bits from our original 32-bit virtual address. And then the page number is divided, or I'm sorry, the fields are then divided into a first level and second level of our page tables. So we really call this like 2-level tables. And so if we look at the diagram here, and it is kind of simplified, because a real page table would contain a lot more information about the address translation process than just pointers. But if we take a look at this, the structure of a real page table includes, a lot more pointers and things like that. But this is fairly simplified. So we have our main memory. We can see that 19-bit and 13-bit on the physical address. We have our page table base, and then we have a first level page table and a second level page table. So we can break this data up into multiple layers that allows us to work with larger page files in a smaller way. So if you want to take a look at something just slightly more complex, this figure right here illustrates the PowerPC's address translation table and kind of gives us an idea of, when I say it's more complex, kind of the more information that would be in the structure of a real page table. So it would have a descriptor that points to the next level in the hierarchical address translation table. It would have, the final descriptor in the chain that points to the actual physical page and contains information that the MMU requires about the page. So in practice, a typical memory management unit may contain table descriptors, and we have several table descriptors of different types. So a descriptor type tells the memory management unit whether another level in the table exists or if we're just working with single level page files. We can have things like write protect, which indicates pages pointed at by this descriptor may not be written to. So if W equals 1, then all subsequent levels of the trees and their associated pages are write protected, so they're read only. U for used, which is initially cleared to 0 by the operating system when the descriptor table is set up. So when the descriptor is accessed for the first time, the MMU automatically sets this to 1, and then the U bit is used in virtual memory systems when deciding whether we need to write back to a physical page to disk when it's swapped out. Then we have things like S, and so S stands for supervisor bit. When the supervisor bit is set, pages pointed at by this descriptor can be accessed only from the supervisor mode. So that would be like operating system level privilege. And the supervisor state is the state in which the operating system runs. It has the highest level of privilege from any user state. And so this would be things like input outputs for disk drives, writing to specific blocks of memory that only the operating system should be accessing. Things like shared globally. So when set to 1, this bit indicates that the page descriptor may be shared. So all tasks within the system may access the physical page. And so this gives us a little more access into whatever this is holding. We can have write access levels, which indicates the minimum privilege level allowed for pages located within this descriptor. Same for read access level. Limit. The limit field provides a lower and upper bound on index values for the next level in the translation table. So the limit field restricts the size of the next table down. And there's an example here. One of the logical address fields may have 7 bits and therefore will only support a table with 128 entries. However, in a real system, you may never have more than like 20 page descriptors at this level. So by setting the limit to 5, you could restrict the table to 32 entries rather than 128. So some further descriptors we can read about: lower and upper determines whether the limit field refers to a lower bound or upper bound. We can have modified, which indicates whether the corresponding physical page was written to. Lock bits indicate whether the corresponding page descriptor should be made exempt from the MMU's page replacement algorithm, so we don't get rid of it, it's locked. And then the cache inhibit bit indicates whether or not the corresponding page is cacheable. So we have reached the end of Chapter 9. Now, we didn't cover all of Chapter 9, but really, I think we've covered everything that I wanted to talk about in terms of what I feel is necessary for the understanding of someone in a beginner course on computer architecture, right? So we use memory to store instructions and data on a computer. And because of the nature of technology and the manufacturing processes, there's no single device or technology that can yet fulfill all of the needs of a personal computer or workstation. Right? In the simplest terms, if memory is fast, it's expensive, and if it's cheap, it's slow, and for a lot of reasons, we don't have a better solution. And I say that a lot, when we were talking about CPU architecture, we, in many ways, feel inhibited or stuck in our development of computers because we want to advance, we want faster, we want cheaper, we want to figure it out, but we're limited by manufacturing processes and other things. And so we learned about fundamental types of memory in a computer, right? How they all relate to each other. And we've examined several aspects of cache memory, such as how it's organized, how that data and physical memory can be mapped onto a location in a much smaller cache, why we use caches in the first place, right? We talked about virtual memory, how hard disks are slow, right? Many orders of magnitude slower than the DRAM in the main store, and how virtual memory systems divide memory into pages of typically 4 kilobytes, which are loaded from the disk drive. And we talked a little bit about the memory management unit and how it plays a role along with your operating system in making this whole complex system work. So thank you for joining me talking about cache memory and virtual memory. I hope you've enjoyed. I will see you next time.